Hello. Today, my partner Sondos Osman and I, Nassif Jabbour, will be discussing the basics of RISC-V for our 3-to-1 project. First, we're going to start with a brief introduction on RISC-V. What does RISC-V stand for? RISC-V is a reduced instruction set computer and it's the fifth version of it. It is an instruction set architecture, an ISA. This means that it defines the software interface for hardware. Therefore, it defines the sets of instructions, the data types, the registers, the addressing modes, the inputs and outputs, and a lot more. We're going to briefly also talk about the origin of RISC-V. Krist Azanovich is a student at Berkeley University and started it with his group as a 3-month summer project in order to create a simpler ISA. This 3-month project turned out to be a 4-year project, and in 2014, the first version of RISC-V was released. It has a lot of predecessors such as RISC-1, RISC-2, RISC-3, RISC-4, and RISC-V. Here we're going to talk about the advantages of RISC-V. First of all, it is simple because it is far smaller than the other ISAs. It has a clean slate design because it has a clear barrier between the user and the ISA, and it is not technology dependent. It has a modular ISA because it has a small base and a lot of options and extensions. It is designed for extensibility because it has a very variable length instruction encoding and it has a vast opcode. But most importantly, it is open source. This means it is free to download the design files and we can build a design free of IP and licensing restrictions. Here we are going to talk about the base and standard extensions. First of all, the base extensions. We're going to first talk about RV32I. This means that it has a 32-bit integer. RV64I, 64-bit integer, and therefore RV128I, a 128-bit integer. Here I stands for integer, and for the RV32E, it's actually a subset of the RV32I, but with only 16 bits. Now let's talk about the standard extension letter. Usually, it starts with the base, and we add a standard extension letter. M is for multiply and divide, A is for atomic memory operations, F, D, and Q are for single, double, and quad precision floating points, G is for general purpose ISA, and C is for a compressed 16-bit version. Registers in RISC-V. There are 32 registers in RISC-V. They start from X0 to X31, and there is an additional 32 registers for floating points. They start from F0 to F31. It is important to note that the X0 register is the only one that you cannot modify. It's actually a hardwired 0. All the other registers can be modified, but these are the usual conventions that are used, such as for X1, it's the return address. X2, X3, or X4 are different kinds of pointers. X5 and X6 and 7 are temporaries. X8, X9, and also X18 to X27 are saved registers. X10 to X12 to X17 are function arguments, and X28 to X31 are actually the temporaries. Instructions format. First of all, we're going to talk about the RISC-V instruction format and then compare it to the MIPS instruction format that you already studied in class. It is important to note that in the RISC-V instruction format there are 6 types. The R type for basic arithmetic instructions, the I type for immediate and load, the S type to store values, the B type for branching conditional, the U type for upper immediate, and the J type for an unconditional jump. Now let's discuss the fields in the RISC-V instruction format. We first of all find the opcode, then the register destination, then the register operand 1 and register operand 2, and function 3 and function 7, which help determine which operation it is going to run. It is important to note that RISC-V is little endian. This means that it starts by executing the least significant bit first. This creates a huge difference compared to MIPS that is big endian. RISC-V being little endian means that the opcode is executed first, and then it continues executing in this direction. In MIPS, since it is big endian, it executes in this direction, also with the opcode first. But the functionalities of the RISC-V instruction format and the MIPS instruction format are very close to each other. In fact, the R-type functionalities are the same as the R-type in MIPS. The I-type functionalities are also the same as the I-type in MIPS. The S-type that stores values are also in the I-type in MIPS. And the branch conditional type, B-type, are also found in the I-type in MIPS with branch if equal and branch if not equal that you already studied in class. And the J-type functionalities can be also found in the J-type in MIPS. Memory addresses. We have two kinds of memory addresses, memory byte addresses and memory word addresses. We're going to first of all talk about memory byte addresses. In this case, every byte is placed in an address in the stack. For example, BZ byte 0 is placed at byte address 0 in the stack. Byte 1 is placed at byte address 1 in the stack. Byte 2, byte address 2 in the stack, and so on. The byte addresses are always incremented by 1. It is important to note that 4 bytes are equivalent to 1 word. This brings us to the memory word address. Memory word addresses are actually formed by several memory byte addresses. For example, for word 0, that is 32 bits long, okay, we can assign it a word address of 0, word 1 a word address of 1, word 2 a word address of 2, and so on. But the respective equivalent byte address of word 0, since one word is composed of 4 bytes, the word 0 becomes 0, but the byte address of word 1 is actually incremented by 4 and becomes 4. The byte address of word 2 becomes 8, and so on.
Just like every ISA, RISC-V has a set of instructions which are the language of the computer, and these instructions are used to execute some sort of procedure, maybe follow a code, and therefore get an input and an output, just like we saw before. A lot of these instructions are very similar in not only format and structure, but also in action as the ones we've studied in class when studying MIPS technologies. Notably, we have the instructions add, subtract, add immediate, load and store word, etc., which are all of the same type and look of MIPS, as well as some logical instructions such as OR, exclusive OR, and etc. We also have some shifting instructions, some branching instructions, and some pseudocode instructions. In the next part, we will focus mostly on some of the features or maybe instructions that we did not see in class. Just like every other ISA, RISC-V has add and subtraction instructions. And what these essentially do is that they take the content provided in the two registers and they store the output in the destination register that is provided in the instruction calling. However, what is different when it comes to RISC-V is that it has multiple versions, notably the RISC-V with the 64 bit registers, and they have their own special instruction for it. The instructions add W, add immediate W, and same for subtractions are instructions very similar in format to the R and I instructions already defined. However, they differ in the fact that they can only operate on 32-bit values. However, since they are extracted from 64-bit registers, the instruction only operates on the lower 32 bits values found in the registers 1 and 2. When performing the arithmetic equation, if there are some overflows, they will be ignored. And after doing the operation, in order to store it back in a 64-bit register, it will be sign extended. Let's look at some examples. We have the values 2 and 64 and 7, which are 64-bit values in the registers 10 and 30. If we use the instruction add W, it will take the lower 32 bits of each, which are here 2 and 7, 8 digits long in hexadecimal, and it will give us the value of 9. And since the sign is positive, it will be extended to this value and it will be stored in register 6. Similar when it comes to subtraction, we will take the same format, the same values. However, here the output, since we're doing 2 minus 7, the output will be minus 5, and this will give us this output. It will be sign extended to fit into the register, and since it is negative, we will sign extend by adding Fs, and we will store it in the register 6. We will now look at multiplication. Multiplication is an instruction found in MIPS. However, we will look at the twist when we are using RISC-V, notably when we're using 64-bit registers. We know that multiplying two n-bit long numbers, the output will be 2n long, meaning when we multiply two 64-bit values, the output will be 128-bit long, and we'll have to store the output in a 64-bit register just like before. So let's see what happens. There are multiple versions of the instruction multiply. Mul RD R1 R2 is the typical one, and it will store the lower 64 bits of the 128-bit product. So let's see an example. Taking the same numbers as before, 2 and 7, multiplying them together will give us the value of 14, which is E. We will then store the lower 64 bits, which in our case will also be a bunch of zeros with an E in the end. There's also the mul H of similar format, and this is similar, but it will store the upper 64 bits. And here, it only works for signed. It will take in consideration the sign of the number. Mul HU is the same one, but with unsigned. And we also have the mul HSU, which combines the both of them. So, assuming we have -2 and 7, multiplying them together will give us the upper 64 bits, which is 1, -1, which is an F. We will now look at division. Division is an instruction found in MIPS, and it is found very similar in format and action in RISC-V. However, an instruction that we have not seen in class is the instruction of remainder, which is found both as a signed and an unsigned version. It simply gives the remainder of a division. When dividing 7 by -2, we'll get the output of -3, and the remainder will be -1, which is stored in register 4. We will now look at some shifting instructions, and more specifically the shift arithmetic instruction, which is an instruction not found in MIPS. What it essentially does is that it shifts the number by a certain number of bits, either the least significant 6 bits of the second register if it is an R-type instruction, or the immediate if it is an I-type instruction. It will empty the bits in the first register, and it will fill them according to it will fill the empty bits with the original sign bit instead of zeros, or when we're using logical instruction. Here's an example. If we're using a shift right logical instruction, when we shift by 1, we will fill the empty slot by a 0. However, in shifting right arithmetic, since the sign of this value is 1, when we shift right, we will get another 1 since we're filling it with the same original sign bit. And this is a very important instruction since right shift logical cannot be used to divide a negative integer by 2. Therefore, this shift arithmetic instruction is used to calculate power of 2 quotients and products. After studying the architecture of RISC-V, we will see its importance in technological innovations when it comes to real-life applications. RISC-V is emerging in popularity, and it is being used by big companies such as Samsung, Intel, Google, etc. because of some advantages we will look at right now. We've already stated some of RISC-V's advantages. Now, what attracts these big organizations into implementing RISC-V chips is the fact that it uses fewer instructions, and fewer instructions mean less memory space, and less memory space means that the chip or the device will be more efficient and more highly performing, and it will be faster. It also has a frozen ISA, which means that no matter what version of the microchip that is being used, the same code or architecture can be used on the chip no matter what version or what time in the future it is being used, which is not a feature that is found in other ISAs. This will allow software engineers to keep on using and reusing their codes through future generations, and this will help them in improving their code by adding, for example, future extensions without changing the code and starting from 0. And finally, it is an open source, and the fact that it is an open source allows the organizations to give consent on whether or not they want to share their code, and if they do so, since it is licensed, they will be able to see whether or not there has been some malicious intent when it comes to accessing their code, and this will allow them to establish some trust between the people working in the organization and with other organizations. And the fact that it is a free available source makes it much cheaper, and it will allow software engineers from multiple organizations to be able to see other people's work and to evaluate on it and maybe build on these ideas, since there is a lot of sharing between the organizations. A lot of new ideas will emerge, and this will improve the technological world at a much higher and better scale. And finally, since the code is available anywhere, it will help in portability, and therefore portability, security, and innovation are improved with RISC-V chips. We have given a brief introduction on the RISC-V architecture and how the instructions and their format is, and we have seen its importance in real-life applications. And we can see that RISC-V is an innovating architecture that will help the technological world in improving in many fields, and not only in the technical field, but also in medicine, in genetics, machine learning, etc. We hope you liked our presentation, and thank you.